Good evening, everyone. It's wonderful to see all of you here this evening for a special program. I'm Diane Cheseldine, the founder of the Distinguished Speaker Series, and thank you very much for joining us this evening for a presentation that's on a subject that's of vital interest to us all, of course, and that's our health. I would first like to thank all the persons who've been involved in this event, the DSS committee, and especially the chair, Candace Garlock, for her many hours of cheerful collaboration. The media services, Tim in the back, and Nancy here, and the TMCC Publicity Office. It takes everyone working together to create a successful event. I'd like to tell you the genesis of Dr. Gavilondo's visit to Reno. Last January, I was in Cuba on a photography workshop. But when I'm not making photographs, I'm stalking speakers. I was hoping to encounter someone from Cuba whom I could invite as a distinguished speaker, especially at this historic time of opening relations with Cuba. How to do that? I told the coordinator of the workshop about my mission, and he offered to introduce me to Jorge Gavilondo. After meeting Jorge, I knew he would be a wonderful addition to our list of outstanding speakers, especially since he embodies both science and art. Fortunately, he graciously accepted my invitation, and here we all are 9 months later. Dr. Gavilondo is an accomplished scholar with more than 40 years of experience in biotechnology and cancer research. He's also author and co-authored more than 150 scientific articles and 5 books. He has traveled throughout the world explaining scientific discoveries pertinent to his work. We are privileged that he's with us this evening in Reno to share that knowledge and expertise with us. And now, may I present Dr. Jorge Gavilondo.
Thank you. Well, it's incredible to be here. And I already was speaking in the morning about art and photography. So with the same kind of money, they got 2 birds with 1 stone. They have art and science at the same time. And this is a rare combination, but I've found that Candace has been all the time telling me that's what we need, to show people that arts and science can be at some point together. And there's some, let's say, common ground in both areas. I'm going to tell you a little bit tonight, about cancer immunotherapy. So we're going to speak about people that already have tumors. It's not how to prevent tumors using our immune system, but how to, in some way, try to control or cure cancer by using the immune system of an individual that already has cancer. First of all, I have to apologize because you saw my picture in that small pamphlet. The same picture that was used for my photography talks was used for my science talk. And of course, this doesn't look like a serious scientist. So I photoshopped myself. I added like 6 inches, which trimmed me a little bit. I mean, it's wonderful what you can do when you dominate science and art and photography as well. Okay, so Cuba. I was asked by Diane to give you a little bit of information. How come a Cuban is here speaking of biotechnology? Isn't that a communist country, underdeveloped, repression, this and this and that? So I'm going to give you some facts. You can draw your own conclusions. I'm going to give you just some facts. For those that don't know, and you don't have to know where Cuba is, we're very close to Key West. It's only 90 miles from Havana, my city, to Key West. And of course, you know about Guantanamo Base. It's here, okay? Okay, so we're 11 million people, and our life expectancy is now 78.45 years, 80.65 years for females, 76 for males. We suffer women. That's why we die earlier, okay? And that's interesting because when you see the table published by the CIA. Yeah, because the CIA has a report on all these things, has other people as well. You see that Cuba is here and the United States is here. So we're doing a little bit better than Cuba in life expectancy. Infant mortality, another very important parameter. We have now 4.2 deaths per 1,000 born alive, and the United States has 5.87. So we're a little bit better there as well. Literacy, we're 99.8% of the population. It's estimated that we had from 20 to 60% illiteracy in 1959 in the country. And you can see the color of the different countries. And of course, the darker ones are the ones that have best coverage. And our children in school are 97.5% of the kids that are till 14 years old are in schools. 12th grade is obligatory. So we have from primary school to 12th grade free education, and it's obligatory. Doctors per inhabitant, 6.7 per 1,000. After Qatar is the second country in the world. And it's interesting because we also have a university. It's called the Latin American School for Medicine. And if you read down here, among the 10,000 foreign students learning medicine in Cuba from 120 countries, we have Americans. There are 100 that already have graduated from Cuba and another 100 that are studying there. This is Lillian Purcell from Oakland, studying there. And we're getting, as you see, overwhelmingly young people of color from low-income families, and 1/2 of them are women. That's a program that started after Katrina, after the hurricane, when Cuba tried to send a medical brigade to New Orleans, and it was not accepted by the government, the US government. So the University of Latin American Studies for Medicine, which was already open, started to open places for low-income Americans that wanted to study medicine, and they couldn't do that in this country. Okay, students in all systems, 2.3 million. We have 47 university centers. We have more than 12,000 scientists, which is 15% of all the graduates that we have. There are 115 research institutions in many different fields. And of course, we're spending now a little bit less, but 0.67, 0.42 of the GNP in research and development. This is our alma mater, the University of Havana. And these are not elephants. That's art in the street. Because, this is a person that fabricated all these huge metal elephants and put them in different places of the city in different moments. And they're now on permanent display in one of our cultural institutions. And this is a bird's eye view of the University of Arts in Havana, which is a great project. My son, which is a musician, studied there. He's now a professor of composition at the University of Arts. Okay, so what about biotechnology? Well, those that don't know that, in Nature, which is one of the most prestigious journals in science in the world, in 2009 was publishing that Cuba had the most established biotechnology industry of all developing world and was growing very fast. And it could seem like crazy how this happened. How come Cuba has a biotech and pharmaceutical industry? And I would tell you a little bit of the milestones for that. I think that the first important thing was to have a national campaign against illiteracy in 1961, very early. So we were showing people how to read and write. That's the first step. Then the Academy of Sciences was reactivated. Our Academy of Sciences is the first one in the whole hemisphere, okay? The first one. It started in 1728. In 63, the Scientific Institutes of the Ministry of Health, a little bit like the NIH you have here, was founded. In 65, we created the first center for research that will be used basically to create PhDs for postgraduate studies and to form scientists as well. In 1980, so let's go in between 81 and 65, during the Carter administration, the governor of Texas visited Cuba. And when he asked Castro, who do you want me to bring with me? He said, scientists, bring some scientists, some medical doctor. And Professor Lee Clark, came to Havana. He was the president of the MD Anderson Tumor Institute and Hospital in Houston. He came to Havana, and he spent hours with Castro convincing him that biotechnology was the industry of the future. And Castro, well, took the bait with the sinker, with the line, with everything, and decided that we already had a number of PhDs formed in Cuba. We had several good universities. Why not create a group that would start the biotech industry in Cuba? And that's what's happened. There was a house, a prodigal house in a very nice neighborhood, and it was turned into a lab to start the biotech program. And their first task was to produce, in that moment, what was called as leukocyte interferon. It was not a recombinant product. It was extracted from blood donations, but it was like the wonder drug in that moment. People thought that apart from being used for viral infections, it could be used also for cancer and other things. And that was our model molecule to start our program. In 1981, also we created the Biological Front, a group of institutions, different institutions that would collaborate. Instead of compete, we would collaborate in this program. In 1986, we were able to create the Center for Genetic Engineering and Biotechnology. For many years, the largest biotech institute in all developing countries. That's what I worked for 28 years. I will share a little bit about that. And there was a huge investment program for a country so small from 90 to 96 to create dozens of production and research and development centers in Cuba. We created then the West Havana Scientific Pole with 51 organizations and more than 1,500 researchers. And then after that, we created the bureaucrats. We created the Ministry of Science, Technology, and the Environment. If you create the minister first, nothing would happen. So you first create the things that work, and then you bring in bureaucrats, okay? So I got a lot of friends there. I'm sorry about that, but anyway. So what was the strategy? Cuban government was going to be the main investor. Based on Cuban scientists and professionals, we were not bringing anybody from any country in the world. We were going to do that with our people. The national health system problems were the first priority, and this is how we die. Many people say that we live like poor people and we die like rich, and it's true. Malignant tumors, in this moment, is the first cause of death in Cuba, more than heart diseases, which is the second one, then cerebrovascular diseases, influenza, like infections and pneumonia, and then accidents. So those are the main problems that over which we focus our work in our biotech program in Cuba. The other thing was to do closed cycle strategy. That is, if we do research and somebody else converts that into products, we're not gonna do good, you know? It's what happens in many developing countries. They have excellent academic centers, they produce a lot of information, and then the products are made in Europe or in the States, and then they're sold in those countries afterwards. So it had to be a closed cycle from research, development, production, and marketing, the whole cycle. That's what. And then, of course, natural collaboration instead of competition, and coordination between different R&D institutions doing research and others applying results. And this is the West Scientific Havana Pole. It's like, 15 different institutions from different areas that all coordinate and collaborate efforts. Some of these are production centers, others are research, some do research, development, and production. We coordinate problems, and we follow a common strategy just by meeting and having no bureaucrats present. Again. Finally, spin-off commercial companies. Each of these institutions was able to create their own marketing department, which was converted afterwards in a small state-owned commercial company, that would sell the product. We were starting to understand what's this business about biotech in the world, okay? And we were like gaining slowly international competitiveness by quality, production volumes, cost, novelty, and joint ventures with other countries, and intensive building capacity for R&D and production. Just as an example, these are the 13 vaccines that we produce in Cuba. We have an extensive coverage for children's vaccine that involves 13 different vaccinations. And all these are produced in the country. We only import polio, BCG, and MMR. The rest, including Hib, hepatitis B, and other ones are produced in Cuba. So we were able rapidly to have an impact in our health system. We have now eradicated many of these diseases. We haven't had a case in the last 4 years of hepatitis B because all the population beyond 20 years old is vaccinated now for hepatitis B, for example. And there's some examples like that. And finally, 2 years ago, the big group, BioCuba Pharma, was created. It was given an autonomous status by the government, so it's a state institution, but it's self-sufficient. So it's not getting any money from the states. You sell, you operate. You don't sell, you crash. So the market rules apply here. It's very interesting. We have 18 institutions there. Many from this Havana Scientific Pole I told you, plus Quimefa, which was a company of the Ministry of Health producing generics, basically, pharmaceuticals. And that's what we have now. And it's exporting already in 2015 $1 billion USDs. And it's turning to be like the second industry in Cuba, bringing a cash flow into the country. Tourism is the first one. Mining is now competing, which was big in the past. It's now competing with, we're now competing with mining. Okay, so that's the center where I work, the Center for Genetic Engineering and Biotechnology. We're like 1,300. We're many R&D labs. We have production plants. We have areas for animals because we also deal with agriculture. We have greenhouses, and we have 2 satellite centers in other places of the island, one devoted to diagnostics and the other one that develops vaccines for agriculture, for cattle, basically. And this is a bird's eye view of the center. We deal with medical biotechnology. We deal with infectious diseases, cancer, cytoprotection, autoimmunity, and in agro, we deal with plants and animals. Our production facilities are state-of-the-art. We have been certified by WHO for several vaccine productions, so we can compete in all the markets now. And these are our products: vaccines, pharmaceuticals, diagnostics, and agro. And most of these products are recombinant. We don't do extractions. Many people think that because I come from Cuba, they're asking me, are you going to tell us about plant extracts of the jungle in Cuba? Where there's no more jungle in Cuba. The Spanish burned that and whatever, so we're trying to reforest the country. And we're doing some extraction products that are trying to be then separated, isolated as active ingredients. But most of our work now is a derivative from scientific studies, basic cell biology and biochemistry studies of whatever disease we're facing. So that all this is recombinant, and probably only this agriculture bionematicide is a natural product. The rest is recombinant. And this is our main product now, the one that is selling the most. It's a treatment for deep feet ulcers. That's a great problem with diabetics. And diabetes is now like the new pandemic in the world, especially type 2 diabetes because of obesity and other problems in the population. And this is a product that had been patented in the US as a molecule, but never got beyond lab. It's epidermal growth factor. And in Cuba, what we did was to produce it by recombinant DNA techniques, and at the same time invent a new way of applying this to the skin. This is a factor that will let you regenerate your epidermal tissues. So the difference is it was normally in the first trials applied as a cream or a paste on top of your stuff. And we learned after many studies that the product will never get into the right tissue doing that. So we inject it directly into the ulcers. And so we work with angiologists at the same time. And the results are amazing. That's the things we treat. You can see deep ulcers. And after treatment, we can recover things. Those feet would be chopped off from people. So this is a great product. We're now discussing with the State Department a license to be able to start clinical trials in the US. The Congress has acknowledged that there's a huge problem here in the US. This is the only product that we have in the world for this. There's no competition. And hopefully we will start clinical trials in the US, but it's already been sold in like 20 countries. It's a matter of time. Okay, the second thing we do is this 5 vaccines in one single bottle. And that's another new product because when you vaccinate kids, you don't want to give them too many shots. So we have 5 types of vaccines in one single shot. And that's another product that is selling very well. We have registrations in most of the countries, except the US, of course. Our patent strategy is to patent everywhere. We have a ton of patents in the US and in many countries as well. And we have done a lot of technology transfer. We have built centers, production and research centers in many countries using this South to South collaboration in Brazil, in Venezuela, Vietnam, in China, in Algeria, India, Iran, and South Africa. So that's our center, that's how our work goes, and this is the future. This is my last slide regarding the center. We're working in infectious diseases. This is a nasal hepatitis B vaccine for people that already have hepatitis B. It's going very well. We're working on the dengue vaccine, pertussis vaccine, and of course we're working also in HIV vaccines and infection inhibitors for that terrible disease. Cancer, we have a ton of projects in cancer. Cytoprotection and restoration, we're trying to develop some peptides that will protect or repair damage in neuro and cardiac diseases, and other products as well. Okay, that's the center. So let's return back. That was like the first course, just to give you an idea of how come I'm talking to you here. And I'm going to try to touch now the main subject of my talk. And remember, we have been treating cancer basically for many years with surgery, which is very effective when it can be done, with chemicals, with chemotherapy, which is very effective in many cases, but it's very toxic, and with radiation, which again is very toxic, but it can be effective as well. And we want better things. And one of the ideas that we're trying to move forward is that even in a person that has a cancer, we can stimulate our immune system to try to control that cancer. Let's think about this situation. For those of you that are diabetic, you're not going to be cured, but you can control your disease, and you can have a quality of life, and you can live many, many years. Where we're trying to convert cancer in something that you can control the tumor. Best case scenario, you cure the tumor. Worst case scenario, you live with your tumor with enough quality of life, as long as possible. And that's what we think we can achieve using our own immune system. So I will give you data, not only produced in Cuba, but in the world, about how this field is moving, because it's very exciting, and I will put some news that I have seen in these days just browsing your newspapers and your news and whatnot. Okay, burden of cancer. You know, cancer is growing every year in all the developed countries, France, Germany, Italy, Japan, Spain, the US, UK. It's growing everywhere, okay? It's expected to double the burden of cancer by 2020 with respect to the beginning of the century. And many people think that this is not a problem. It's the main problem you have. Because when you see cancer as one of the principal causes of death in different ages, among the first 4 causes of death in the United States, cancer is present in all age distributions. So it may not happen like it will not be the first cause of death in these ages, but it's the second cause of death. It's the fourth here, it's the fifth here, it's the second here. And we know now that even though probably in many countries people die preferentially of heart disease, the disease that takes more lives of effective living from humans is cancer. Because heart disease concentrates where? In old people or people after 40. Nothing happens in all this area. Cancer is there. Okay, so cancer is a very important problem. And it's not a problem only for developed countries. People think that that's a problem in the United States or the United Kingdom. It was not a problem in developing countries. In 1970, only 15% of new cases were reported in developing countries. In 2007, 72% of the cancer deaths are in our developing countries. And by 2020, 60% of the new cancer cases will appear in our countries as well. So it's a world problem. Everybody has to study and to contribute to solve or try to control this problem as well. Okay. Have things advanced in this field? Of course. Medicine are transforming the treatment of many diseases, and of them, cancer. We really have new therapies that have given us like 20% less cancer death than many years ago. Things are advancing. Not at the pace we want, but they're advancing. 5-year survival rates since 1975, 21% more in breast, 50% more in prostate, 36% more in colon, 54% more in lung, which is the big killer. That's the big killer in men. That's the big killer in women. This is very important, and of course, prostate cancer is very important in men as well. So things are improving, and in the last decade, we have seen among the many advances, we have seen here in 2004 new drugs for colon cancer and for lung cancer, kidney cancer, lymphoma, this is melanoma, the first therapeutic cancer vaccine. Many of the advances that we can record that have happened in the last decade are in cancer. We got to do more than that. Childhood is one of the great examples. 58% survival has increased in children since the mid-70s. Leukemias and lymphomas are better treated now than many years ago. Survival is real now. So when people think that cancer cannot be cured, cancer can be cured. It can't be cured as we would like in all the cases, but we have been advancing. And when you see what is being developed now in the world, these are many, this is a report from the Pharmaceutical World Association, and these are different diseases. In cancer-related and related conditions, most of the medicine being developed in this moment are precisely for cancer. Second, infectious diseases. So this is a priority for the world in this moment, okay? And it takes a long time, and we wanna shorten that time. You can have tens of thousands of compounds getting into drug discovery, of which only a limited number will get into clinical trials, and then over 6 or 7 years, we will finally see one approved by the FDA or the EU. Is this bad? Well, it's not what we expect, but again, it's a way of assuring that what you get is something that will not harm you. And even though there are many complaints about the speed in which the FDA approves new drugs of important diseases, there has to be a regulatory body that will keep you out of snake oil preparations. That's very important. So there's a balance there. We gotta go faster, but we cannot get into our pipeline, into our approval, things that have not been proven. One thing is what you think for yourself or your personal experience, and the other thing is to say that this product will serve the world community and can be sold freely without any problem, okay? Anyway, this was one of the news. 3 big drugs likely to hit the market. That was September 30. And one of them has to do with a non-small cell lung cancer, one of the killers, and it's Keytruda, which is one of the drugs I'm going to tell you about. It stimulates the immune system. That's another one. Roche, cancer immunotherapy news is going to turn some heads. That was yesterday. Again, some drugs. I'm going to tell you about what's happening. What's all this excitement that is happening here, okay? Anyway, first of all, let's start from the beginning. What's a tumor? Well, I ask people, what's a tumor? Well, it's something that is, growing, like a bump or something, and suddenly it goes crazy and starts invading and setting itself in different areas that are not the place where they started. So that's the local growth and the secondary tumor site, the metastasis, what we call. And this is the worst part of it. If everything would grow on a site and we could remove that, surgery would certainly do the job. But by the time we diagnose and we apply surgery, some cells have already gotten into the blood and have migrated to other tissues. So that's what we know, that's what we see from cancer. Now, what we've learned over the years is that cancer cells, when students ask me, how do you define a cancer cell? And I would say, well, it's an abnormal combination of normal elements. How come? Well, you see, a cancer cell has 2 heads, 4 limbs, and 6 feet. It's abnormal, but it doesn't have wings or tails or scales. It has things that are already present in normal cells as well. So it's the combination of different traits that are also present in normal cells, what we have abnormally in cancer cells. And that is why it's so difficult to kill them. Because if we have an anti-limb antibody, it will affect the cancer cell, but it will also affect the normal tissues, and so forth. So we're trying to somehow navigate in this hard area in which there's nothing more similar to a normal cell than a tumor cell. They both are the same. They're not bacteria, they're not viruses, which are extremely different, and we can use antibiotics to kill bacteria because at those doses, normal tissues will suffer very little. This problem is very difficult, extremely difficult to solve. Okay, so when we see which are those traits, well, we see that suddenly the cells proliferate without control, or they should die, they don't die normally, or they induce blood vessels to grow towards the tumor to feed the tumor. What's that? That's strange. Or they evade all the growth suppressors that we have circulating in our body, or they activate that kind of invasion and metastasis behavior that is not normal for some tissues, and they're immortal. They will replicate and replicate and replicate and replicate. And we have medicines now for most of those things. We're targeting most of these things, angiogenesis and proliferation. We're developing now things that will let cells, tumor cells die, and others that will control metastasis, and others that will make growth repressors that we already have be more effective. But that's only happening in this moment. Now, are these the only traits that we have in cancer cells, the new things? No, they're emerging hallmarks as well. They have different energy sources. They're using less oxygen. They have a different metabolism. And of course, if you dig, there's a normal cell in your body that uses that kind of behavior as well, okay? Only it shouldn't happen in the tissue where you have the tumor. It should happen somewhere. Or it should happen when you're a fetus, not when you're an adult person like that. And the other interesting thing is that tumors avoid the immune destruction, and this is not working. Okay, tumors are avoiding immune destruction. For many years, we thought that the immune system would only work against viruses and bacteria, not against tumor cells. And there were many discussions about this. Now we for certain know that our immune system is killing cancer cells all the time. So that's one of the reasons why, even though we already have a growing tumor, we think that we can boost our immune system to do some kind of job there. That's the main reason why. Okay, so avoiding the immune system is what we want to prevent, and that's the rest of my talk. Okay, so how do a normal cell turns into a cancer cell? Well, this is the normal tissue, and because of carcinogens or radiation of infection, some viral infections, chronic inflammation, and other mutations, you can go from a normal cell to cells that go haywire and start doing things that they shouldn't do, growing and doing other things. Some of these cells regress. So they turn back to a normal state. That happens. Or they die. They're not allowed to continue. They die spontaneously. But there's some that will live, and immediately the immune system starts seeing some strange things. The immune system will detect, oh, there's an abnormal amount of this normal element. Oh, this shouldn't happen in this tissue, or this shouldn't happen in this state of development. The normal system sees that. And if the normal immune system sees that effectively, many cells of the immune system will attack that tumor and will kill the tumor. And in that way, we probably prevent by ourselves many of our cancers. And that's normally happening in each of us, probably during our lives many times. Who knows how many times? However, nothing is perfect. And sometimes from that population, the immune system couldn't destroy. What happens is that resistant cells emerge. And during many years, they become dormant. They're evolving very slowly. So they are not growing as a tumor, but they're there. They cannot be killed by the immune system, and they will remain dormant there until something happens. And that something can be your immune system is down because of something else, or you got an inflammatory thing, or you get an extra stimulus, and suddenly those cells start to reproduce, and they escape the control of the immune system, and then you have a full tumor. And then it's very difficult, because one of the things that the tumor does, because of the way it evolved, is to produce an immune suppression in your body. So the normal evolution of a tumor goes from evading the system to creating stronger cells that will be very little immunogenic, or the tumor produces substances that will depress your immune system. And that's why the tumor grows, and we cannot control that, okay? So that's an easy way from normal cells to already cells. You already have a tumor, so you're in deep problems. Okay, not the other thing, not the other word. Anyway, well, the other word as well. Anyway, so what we have learned is that the immune system at some point, and I'll show you a little bit more about those cells, can recognize tumor cells and their activity and products, can eliminate them, so we can use it. Even in a growing tumor, there's still an active interaction with the immune system. So that means that if we can enhance that interaction by using molecules, immune cells, or immunization procedures, we might control cancer. Let's see what happens. Okay, so these are the good and bad guys. That's the bad guy, the tumor cells. This is a very interesting cell we have all over our skin and different parts of our body, which is called the antigen-presenting cells. Those are the cells that eat debris and present those molecules that are dangerous for us, so that the B lymphocytes or the T lymphocytes will see them and attack their targets. And you know how the system works. It's very interesting. When I ask sometimes my students, how do you think the immune system works? Like a retail store? Or that, well, you go there and you go to a rack and you buy a pant. You have many sizes there, so you can choose a pant that fits you, and that. Or you go to a tailor that measures you and makes that pant. And how do you think? And many people say, oh, it should be like the tailor. So a strange substance gets into your body. There's a cell that sees that and starts building something against that. No way. It's the other way around. From the evolution point of view, it's easier for you to have millions of cells that are already predetermined to see different strange things that will get into your body and react immediately. You don't have to wait 2 weeks for the tailor to make your pants. You get your pants, you put it on, and you're rolling, okay? So that's the way it works. But for that, you need evidently some cell that will tell you, okay, there's something strange in our body, interact with these cells, and then either kill them directly, kill the tumor cell, or produce antibodies that will indirectly kill the tumor cell, okay? And this is a little bit what happens, okay? Those APCs instruct other cells, those other cells instruct cells to kill directly tumors or to produce antibodies, and this is not working, it's working again, okay? So we have to use for immunotherapy these cells, or enhance their activity, or produce the soluble products that those cells produce. And that's the whole field of immunotherapy, trying to get this knowledge from the immune system and try to attack tumor cells using products from many of the angles that the immune system uses to defend ourselves against tumors and against other things. Okay, I will talk about 2 aspects of cancer immunotherapy. There are many, let's say, angles to this thing. I will tell you about 2, which are the most exciting ones. And please understand that we're facing now a problem of specificity. When you're not sick, and they tell you, boost your immune defenses with a pill or with vitamins or who knows what, that's okay to do this general boosting of your immune defenses. But when you have a tumor, those general immune, augmentation drugs or pills or whatever will do very little. Because what you need is a specific immune response against your tumor. You don't need a general feeling that your immune system is a little bit better. You need the immune system to target directly what it has to kill. And that's why I will talk about specific immunotherapy, not non-specific. It's not to have a shot of BCG because it should give you like an immune boost, or have gamma globulins, or have other things. I'm not going to talk about that. It's not that they're not useful. I think they're mainly useful when you're healthy, and they're much less useful when you're already sick. When you're sick, you got to go to the target and be specific. So I'm going to talk about cancer-specific immunotherapy, and one of the things we're using is antibodies. Those antibodies you saw that were produced against tumor cells, we're going to produce antibodies. So what's this antibody deal? Well, antibodies. What are antibodies? Antibodies are molecules that navigate our blood. And they're wonderful as a structure. This is a crystal structure of an antibody. And this is a scheme here, and it's like a Y. And it has two parts. This part that will see the foreign thing, what we call the antigen, and will bind to it, and will neutralize it, or will remove it from our body. And this other part, which is a signal telling other cells and components of the immune system, come here and do your job as well. So the antibody needs help, okay? So it's a great molecule. And I've been working in antibodies for 40 years, 30 years making genetic engineering, creating incredible constructs, new types of antibodies that have, instead of these 2 arms, like 4, or have 2 legs, or are a little bit shorter because you want them to navigate faster in your blood. There's marvelous things you can do with antibodies. They're special drugs. Now, who produces these antibodies normally? B cells. And these B cells you have here, you have an antigen, a strange thing. This B cell doesn't see that antigen. It has a different receptor. This one sees it, and the one that sees it is stimulated, gets a little bit of help, and then converts in what is called a plasma cell, a big sack of antibodies, which dies and releases the antibodies. And that's how normally it happens, okay? And when you inject a mouse, for example, or a human, with a given molecule, let's say you're injecting the mouse with a complex molecule that has several parts, a big molecule, several different clones of the B cells will recognize different parts of that molecule. They're predestined to recognize them, and each of them will produce different antibodies. And what you get when you bleed this animal, or when you take the blood and you separate the serum from the cells, is what is called a polyclonal antibody preparation. You have different antibodies produced by different clones of cells. Now, that is good, for example, and it's used nowadays when you have antivenoms. Those are made in horse, by injecting horses with snake or insect venoms. And it's good because there are many components in the venom of a snake or an insect or another arachnid. And it's difficult to separate those antibodies. It's better to have that pool of things there that will be effective against the many neurotoxins that one of those venoms has. But for cancer, we need more specific things. We can deal with a polyclonal antibody. Now, in 1975, these 2 guys, Cesar Milstein, Argentinian, and George Keller, Swiss, discovered an amazing technology that revolutionized immunology and science. It's called the monoclonal antibody production. You could say, well, Jorge, what about if we take one cell, one of those B cells, separate it, put it in a flask, grow it, and that cell will only produce one kind of antibody, if you're trying to separate that kind of thing. Well, that's a great idea, but that doesn't happen. The cells go to plasma cells, produce antibodies, and die. They will not live forever. You cannot reproduce them at will in a flask. So what these guys invented was to take those cells and fuse them to tumor cells that reproduce forever. So you had hybrids now that had the information of the antibody plus the information of the tumor cells reproduce forever, reproduce in flasks in animals, wherever you put them. So suddenly you have here now immortal cells producing antibodies. And now you can separate one cell, the other, and the other, and put them to grow separately. And what you have at the end is monoclonal antibodies. So when you hear monoclonal antibodies, you're going to be hearing this because most of the drugs that are coming now are monoclonal antibodies. Now you know what is a monoclonal antibody. And we owe these two guys that are dead by now that amazing discovery that have given us a way of controlling part of our immune system, at least the antibody part, and making at will many types of these wonder drugs. Okay, antibodies are important. Look, against when you see all the biologics that are being developed for cancer, 338 products are based on what? On monoclonal antibodies. More than vaccines, more than any other type of drug in the biotech field are antibodies, this kind of antibodies. And that's because it's amazing the strength these molecules have. They can specifically see many things, abnormal things. You can even distinguish a single atom in one molecule with an antibody. So powerful has our immune system evolved over the millions of years. Are we using mouse monoclonal antibodies now? No, we're using basically fully human ones. We cannot immunize humans, take their spleen, and make those techniques. That's not ethical and it's not possible. So we're using genetic engineering to transform this mouse and rat antibodies that we can make in the lab and take out the smell. You know, they smell like mouse or rat, and make them fully human. And that's because if we inject mouse antibodies, the body will see that it's a strange thing we're injecting, and our immune system will remove those antibodies. It will not be so effective. So over the years, we have gone from totally murine, rat and mouse products, to fully human. And we're doing that by a number of techniques I won't tell you, but it's simply amazing. When you want to make an antibody in my lab now, you don't use anything but a freezer. You open the freezer I have, take a small tube, and say, okay, what kind of antibody you want? Well, I have this antigen, this strange molecule. Okay, and you put whatever I have there against that, and you have a living organism that will produce antibodies against that. You never immunize animals or humans anymore. You have what is called a library in a test tube. And you pick up from there fully human antibodies that have been made by recombinant engineering. Okay? Anyway, that's interesting. Now, are these important? Hey, you have here in the US 47 antibody products already in the market that are used for many kinds of diseases. 18 of these products have annual sales of over $1 billion. 6 of these products, Humira, Remicade, and Brel, you have seen those in TV, Humira for people with autoimmune diseases and inflammation and whatnot. Rituxan for lymphomas, Avastin for colon cancer and others, Herceptin for breast cancer. Those are monoclonal antibodies, fully human monoclonal antibodies. They had sales greater than $6 billion. So that's a great thing. And if you want to know what happens with you guys now, what you have here in stock, you have all these antibodies, okay, for use. Only for cancer. I'm not talking about the other 40 or 30-something antibodies used for infectious diseases, for autoimmune diseases, for inflammation, and for other states. This is only for cancer, what you have here. These ones are now in revision in this moment. And this is the Keytruda. That's one we showed at the beginning of one of the news. Okay, it's being used for melanoma. In this moment, I'll show you why it's very exciting. And other ones that are being done for melanoma and cancer and lung cancer as well. Okay, so which are the targets these antibodies are directed to? Which are? There are different kind of molecules. They're not completely specific to tumor cells because it's difficult to find something that is in a tumor cell that you won't find in other normal tissue in your body. It's practically impossible. That's why you always have a level of toxicity, okay? Because you're killing tumor cells and you're affecting also a normal tissue, because what I told you at the beginning. Let me put you an example. This is the tumor cell. This is the tumor cell, and displays in its surface a receptor, something, a molecule that it's needed for the tumor cell to get a signal and reproduce? Well, you can use an antibody to block that receptor and recruit some other immune system components to kill the cell. So that's a way some antibodies work. For example, the anti-lymphoma, the Rituxan, works in that way. Now, let's show you another one. Let's say that the tumor cells need to grow, having a receptor receives a growth factor from your blood. So this interaction will make the cell grow and reproduce. Well, you can always block the receptor with an antibody. So the ligand, that growth factor, will never reach the tumor cell, and the tumor cell dies. That's another way, by blocking the receptor. Or you can simply block not the receptor, but block the ligand, the soluble thing. Instead of blocking something on the cell, you remove from circulation that growth factor. And at the end, you can also, instead of using naked antibodies, which is what we have been using to the moment, we can couple the antibodies to radiation or to drugs or to many things, and those are the things that we're doing now with antibodies. Several of the antibodies that are registered and used in many diseases and in cancer have either a radioactive product coupled to them, so they will target that product not to other tissues, but mainly to the tumor tissues, or a drug, or whatnot. Okay? Okay, so I'm going to tell you now, what about these news? Something different. All this, okay, it's part of the immune system, but are we doing something new? This is the exciting part now of what is happening. We're trying now to target with antibodies, molecules that are involved in the normal mechanism of the immune response, used by tumors to escape immune system recognition. It sounds very strange, but it's very simple. The tumor evolves by displaying some traits of immune cells as well. So it will trick the immune system and say, I'm not a target, don't hit me, okay? Regulate yourself because I'm yours. You can't kill me. That's some of the tactics that tumor do, as well as they show other traits of other normal cells, they show also traits of immune cells as well. And we're trying to change that. How do we change that? Okay, remember all the actors here? You have to present the antigens, get the cell activated. This will see the tumor cell, will kill it directly, or will produce substances that will recruit other immune system cells to kill your tumor. How does it happen in reality? This is the way. Let's start by one. Some tumor cells die spontaneously. They die. There are too many. They're crowded. Some of them die. And we release some molecules. And those are seen by those antigen-presenting cells. They digest those molecules and put them in their surface. Okay? It's like a porcupine there with a bunch of things on their skin. And then that cell, which is patrolling everywhere, will migrate to your lymph nodes, and there that cell will interact with the T and B lymphocytes, the ones that have to do their job, either produce antibodies or kill directly your tumor cell. After they're instructed here, they will go into circulation, they will migrate and go to where? To the tumor. And in the tumor, they will see then specifically tumor cells, and they will kill them. And that's what we want to enhance. That is happening even in somebody having a tumor, but it doesn't happen at a rate that will allow us to control the tumor. So we want to enhance that. And one of our problems is that the tumor is trying to fool this cell here. There are two phases here. Important is this priming phase, where the antigen-presenting cell instructs the lymphocytes, and of course the effector phase, in which those instructed lymphocytes will come to the tumor and kill the tumor. And things are happening here, very interesting things. We didn't understand how come, if you're able to instruct these cells and they're ready and active, they go to the tumor, how come they don't kill the tumor? And we were baffled by that for many years. Well, what we know is the following. This is the priming phase. Then the T cells are instructed, they go to the cancer cell. But when they meet the cancer cell also is producing some kind of molecules in their surface that are normally used to dampen the immune response. So you see the lymphocyte sees this thing on the cancer cell, and he thinks, oh, I have to regulate my response. I won't kill this cell. That cell is mine. So it's a strategy to escape, to evade the immune response. So what we're using antibodies now is what? To block either this molecule in the cancer cell or this molecule on the immune cell. And then everything's seen, there's no negative regulation, and the cell can kill the tumor. And the results are amazing. There's a bunch of products against this PD-1 molecule. Remember, there are two. There's PD-1, which is what it comes in your lymphocyte, and its receptor on the tumor cell or in other normal cells, which is called PD-L1, okay? And what happens is that we have now several anti-PD-1 antibodies that are approved, like this one from Merck is approved for melanoma. Melanoma is a very tough tumor, as you well know, and the results I will show you now have been amazing. Just by allowing immune cells to do their job, nothing else. Those antibodies don't kill tumor cells directly. The only thing they do is they let the immune system do what it has to do. Okay? That's the only thing they do. There's some others from Bristol Myers Squibb, and in melanoma, 1 year overall survival rate 69% in clinical trials. Normally, that's 25 or less. That's an improvement of more than 45 points. That's amazing. Head and neck cancer study, complete or partial response in 11 out of 56 patients with advanced head and neck cancers. Lung cancer, 80% of patients with tumor shrinkage. And listen, the antibody is not doing anything against the tumor. It's just manipulating those pieces of the immune system that the cancer cell is exposing to evade the immune response. Okay, other companies are working not in the molecule that is on the tumor cell, in the normal cell, but in the tumor cell, the receptor. And it's the same. This is from Bristol Myers Squibb. This one is from Genentech Roche. And one of the things that I showed you, one of the news was Roche is going to turn some heads and whatnot. It's because their results in advanced kidney cancer still in trials, but they have been outstanding. So we're going to see now a new generation. And when you see what are the antibodies to watch in 2015, we're going to have a number of things here, especially for lung cancer, and they will be tried in lung cancer first and in many other tumors, because we know now that the immune system is working in cancer patients. Only the tumor is evading its effect. Now you see that there's a report of antibodies to watch in 2015, and there's a strange name here. That's a Cuban antibody. So I brought you this because those are the ones you make here in a hugely developed country, but there's one that is made in Cuba. It is called Rocco Tumor Map. That's the generic name. They have really strange names, and is an antibody against one molecule that is present in lung cancer cells, and it works by a very strange mechanism. Look at this. This antibody is produced by the Center of Molecular Immunology. One of my graduate students is the head of this project now. And what the antibodies do is the following. You have a tumor cell here, a lung tumor cell, that shows some strange molecule on their surface. And then what you do is you inject antibodies that mimic that antigen. So it's like providing the body with more tumor cells, but instead of more tumor cells, we're with more antigen, more molecule, the same one that the lung cancer cell has. So the body reacts violently against that thing, and it's also against the tumor. It's called antidiotypic response, and it's an antidiotypic antibody. Now, this is an antibody working in a different way. You immunize people with that antibody. People will react against that antibody, and the antibody mimics a cancer cell. So you're reacting then against the antibody and against your tumor. So you don't humanize that antibody. Keep it smelling mouse. Make it as strange as possible so that the body will see it as something foreign and will react against it. So it will also react against the tumor. And that's one of the antibodies that we're made in Cuba. And we have been working for that in 15 years. It's already in registration in Brazil, Argentina, and Colombia. UK and Australia have their own clinical trials. And there you go. April 2015, you know this guy? Probably. That was a New York Cuba work trade mission, and one of the things you can read here, the Center of Cuban Immunology, the Cuban Center of Immunology and the Roswell Park agreed to bring that antibody to the US and to start clinical trials in the US. And everything's moving in that direction now. So finally, things are getting better in allowing this exchange between Cuba and the US because of the announcement of last December. And I don't know if this antibody will prove to be better or worse than other things, but it's a new drug, patented drug, totally new, novel one, that is made in Cuba and will be available also in the US for starting clinical trials in this country. Okay, so we were talking about vaccines because you vaccinate with this antibody. So let's get to the last part of my talk. And I'm going to tell you now not at what we call passive immunization or passive antibodies, antibodies that you inject so as to kill the tumor cells. We're trying here to activate our own system. It's specific, but again, it's not passive but active immunization. We're talking about vaccination, immunization. And I'm not talking about prevention. There's a number of preventive vaccines for cancer now on the market. And curiously, many people don't know that when you immunize yourself against hepatitis B, that's an anti-cancer vaccine. Because a number of people that are infected with the hepatitis B virus go to liver problems like cirrhosis or hepatocarcinoma. So when you prevent infection with hepatitis B virus, you're removing also liver cancer in a certain amount from the population. The other preventive vaccine that you well know and has been very much discussed in this country are the anti-Hpv vaccines. There has been a lot of discussion, I mean, in developing countries, we sometimes are amazed of the things that are like public discussions in the US. Like the main discussion is, this is a virus that has been shown to be associated with 95% of cervical cancer, okay? That can be carried out by men, but women are the ones that get the cervical cancer. And it has been shown that you can prevent this infection in a high degree by vaccinating young people before sex. So it has to be, first of all, young girls. And I have watched the discussions, how can I vaccinate my beautiful, innocent girl for a venereal disease? For me, that's like a little bit of troublesome, honestly. I mean, please immunize your girls, okay, and your boys, okay? It's, millions of people are being immunized in the world to get HPV out of the scene and prevent cervical cancer in women. Either because they get it some way, they always get it through men. We're the bad guys here, okay? We're the whatever. Anyway, so I don't know why I gave you this commercial, but again, but think about it. Maybe you agree to disagree with me, but I hope that you're rational enough to think that you should protect the population. I also seen this amazing discussions whether kids should be vaccinated or not. And for me, it's like, I don't know, honestly, those of you that have white hair in this place or have tinted your white hair may remember how many people died in the past from infectious diseases. Whole cities and towns were wiped out by a measles infection, by typhoid fever, by many things. And we have affected by polio. We have effectively prevented that. So we're free of those diseases now, and for the common person, that is part of the background. They don't see that anymore. So now we're worried that the aluminum adjuvant that is used in vaccines will create nervous things and whatnot, and 1 in 2 million kids that will be vaccinated will probably have some kind of thing, and the data are not really, not totally certain of that data. It has not been shown, but there's a whole discussion about that. What I have seen is that, for example, in Great Britain, in the UK, there are now measles epidemics that kill kids. Suddenly, after I don't know how many years, without having a single death due to infection. So again, vaccinate your kids. Nothing's going to happen. Come on. Don't be handsy pansies. Okay, so anyway. So let's go to cancer therapeutic vaccines. You remember all this, okay? So the big problem we have is that with a tumor, we don't have now the normal tissue. We have those crazy cells now that are immune resistant. They have developed their way to fool our immune system and to evade the response, and we gotta now try to do something against them. And so we have somehow to work on the tumor cell and select which of these molecules should we put in a vaccine so they will kill as many tumor cells as possible. One of the things that tumor cells do is they change those molecules on their surface. So if they become hidden, suddenly it's immune to the immune system, as we would say. So we have to do something there, and we have to reinforce all other cells that I haven't told you about, which are very important. Our immune system doesn't work like crazy. It's regulated, not by bureaucracy, but by very nice cells. What they do is keep the immune system under control. You should react against foreign things, but to a certain point. You don't want an autoimmunity thing happening. You want to keep your immune system in check. And one of the things, well, there are cells like regulatory T cells or myeloid cells that do that job normally. What cancer cells have learned is to stimulate these regulatory cells so as to dampen your immune system as well. So that's why the battle is very difficult. It's extremely difficult as well. Okay? Okay, so which are the strategies we are now developing to make these cancer vaccines, specific vaccines? First of all, we have to carefully select what on the tumor cell we're going to provide the vaccine with. The second thing is that we always have to add a little bit of immune potentiation or adjuvancy to our vaccine. We have to make it stronger, to make our system react. Because, listen, we are reacting against normal things that are disproportionately appearing in some cells, but they're still normal. Our system has been instructed not to react against those things. We have to overcome that normal reluctancy of the immune system to attack its own things. So we have to do something like that. So we're going to foresee prolonged immunization schedules. It's not to be like a 1 or 2 shot thing like for infectious diseases that you already know. You will have to immunize people with cancer all the time because the immune system will try to quench that anti-self response. You got to immunize again. So that's something we can foresee. And we have to combine. None of these weapons are going to be used alone. We cannot combat things as difficult as cancer only with one of those tools or these weapons. So we'll have to combine that with surgery, cytostatics, and we'll also have to combine antibodies and vaccines and even different kinds of vaccines, okay, to be able to reach our goal. And of course, vaccines against cancer is also an important. These are antibodies against cancer. Of course, the most studied number of products, but vaccines is also a field that is thriving in experiments as well. And there are 2 approaches: personalized and generalized vaccines. What is personalized vaccine? Well, the only vaccine in the world that is registered is a personalized vaccine. It's called Prevenge from Dendron, and it costs like, I don't know, $93,000, 3 shots. Okay, so it's good for prostate cancer. It gives you like 6 months, a little bit more than 6 months extra living. For $93,000, it's nothing. Anyway, what you do is you extract immune cells from a patient. You put it in a petri dish together with an antigen that is found in prostate cancer cells, and you add a powerful stimulant, so you make these cells very active against that cancer, and then you re-inject the patient. And of course, you have to inject this patient. You can use that only for that individual. It's a procedure. It's nothing off the shelf. It's something that you got to do person by person. And that's why, in fact, it is extremely costly, that procedure. Now, that's not what we really want. We want something a little bit more off the shelf, something that we could use in many different patients. It will reduce cost and it will be easier to do, okay? And I will give you 2 examples of that. and we'll end with the work I've been doing for 15 years in 3 slides. Okay, so one example of those non-personalized off-the-shelf vaccine is the vaccine I was telling you about a little bit before, that one developed by the Center of Molecular Immunology, that anti-Therapeutic vaccine. It will see all non-small cell lung cancers. So if that works, it will work not only with one patient, but with many patients as well. And there's another vaccine already in development in Cuba. It's already approved in Cuba and several other countries. Is again for non-small cell lung cancer that uses one normal receptor that is very much needed by those cells to grow. It's also in some normal cells as well. And you immunize against that receptor. So you're making antibodies like hell that prevent that receptor to work in cancer cells. And the balanced toxicity and effect is much, much more important for tumor cells, so you kill your tumor cells. Okay? And both of these vaccines are made in Cuba by the Center of Molecular Immunology. That's the center that stemmed from my group in the National Cancer Center when I was working there. Now I'm going to tell you what I'm dealing with. I'm dealing with a different kind of vaccine. Listen, do you know how tumors grow? Well, of course, they reproduce, the cells divide, and there are more cells. As they divide, they need more blood. That's normal. I mean, they have to have much more blood vessels feeding the tumor. So the tumor starts to produce a substance that is called vascular endothelial growth factor. It's a hormone that the tumor produces to stimulate nearby normal blood vessels to grow towards the tumor. So the tumor is creating its own blood supply. And as the tumor grows and grows, it produces more and more VEGF, and then it's essential for tumor growth and for dissemination of the tumor. And this is well known. This is nothing that I discovered. In fact, there's several drugs now in the market here in the US and in the world that try to either remove VEGF produced by tumors or prevent tumors to produce VEGF or prevent the cells from the normal blood vessel to grow towards the tumor. But they're very toxic because, hey, angiogenesis, which is what we're talking about, is also a physiological process. Every woman in her period will have a physiological reangiogenesis process. When you break down or have a heart attack, or even when you hit, I don't know how many blood vessels are killed, there's VEGF produced normally in those tissues to restore and to maintain my blood vessels. So it's a physiological thing. If you're going to go from the outside, you got to put, to kill VEGF in your body, you got to put tons of VEGF, either antibodies or chemicals. And they have proven to be extremely toxic. What I'm trying to do is something that will kill VEGF, but will be non-toxic. I'm trying to produce a recombinant VEGF that will be seen by the immune system, plus a very strong adjuvant we get from one of our bacterial vaccines, and stimulate the body to do several jobs. The first one is our own body will make antibodies that will block the VEGF that is produced by tumors. So we're doing something there, okay? So we're trying to prevent angiogenesis. The second thing is that we will signal then the tumor cells with those same antibodies for T cells to come and destroy the tumor cells as well. That's something that the drugs don't do. And the third thing is that we're creating cell death in the tumor. And that is an environment we want because that's informing better our immune system that something's happening and other antigens will be seen and other immune cells will attack the tumor. And that's our hypothesis. Is this true? Well, we have just published an article of our first clinical trials. You can check it in Vaccine. We did a first trial with very advanced cancer patients, which have already been out of treatment. There's nothing to do with them. They have gone all over the possible cycles, and that's the kind of patient you use for what is called a phase 1 clinical trial, where you're exploring if your new drug is toxic or not. And we have shown that this is absolutely non-toxic. The second thing is those people had 6-month life expectancy, and of the 30 patients we used, there are 8 still alive after 4 years. from different diseases: duodenum, ovary, neuroendocrine pancreas, seminomas, sarcomas, non-small cell lung cancer. Okay, these are the actual patients. We have been immunizing these guys every month since then without any toxicity at all. And it seems that what happens is that the immune system develops a response. That response works against the tumor and then is quenched immediately by the own immune system. So it's something happening at low scale. It's not a bulk of crazy chemicals or antibodies getting into your body that will create problems to the normal tissues. It's something that is growing slowly in your body, and then it's hurting more the tumor than hurting the normal tissues as well. So we have 4 cases, and let me tell you, all these guys are now working. Some of them are farmers, and 4 of them have complete response. Their tumors have completely disappeared. One has a partial response, and the other ones, they have tumors, but they're in control. So we're now in phase 2 trials. I don't know what's going to happen. We're very excited. We're targeting ovarian cancer, which is a big problem. There are very few drugs, effective drugs against advanced and metastatic ovarian cancer, so we're trying to do our things there now. So I think that vaccines will be very important in your life. Cancer vaccines, therapeutic cancer vaccines. And I think that people, as this US opinion leader told, will be willing to get them, because if they don't have side effects, that's the worst problem about chemo. I mean, when you're getting chemo, what you're thinking is, you know, I'm going to have a terrible recovery if I recover. Now, vaccines in general, how they work, because they are always, you know, being quenched by the immune system, you've got to give them again and whatnot. You have this very, very low toxicity. I can tell you, these guys, after 4 years of vaccination, they don't even care about vaccinating themselves. It's a shot one time in a month in their arm, and that's everything that we get. So we'll see a lot of vaccines against melanoma and other things in the future, and I thank you very much for your attention, and I'm open to any question. So shoot, not a problem. And that's my email. You can email me. Yes?
The obvious thing is going to be cost.
Excuse me?
Cost.
The cost.
It's going to be a major factor, because we've got drugs here that was one last week, and the company, they upped the drug from $50 to $600. So what's going to be your cost on these things? I mean, for you?
The cost or the price?
Well, both.
Because I'm learning economy. If you're in the biotech industry, you have your feet on your ground. And what happens is that, excuse me?
Who's going to be able to afford these things?
Nobody. Something's going to happen, honestly. I mean, all these treatments is thousands and thousands of dollars. And let me tell you how life is interesting in that sense. So we provide the whole health system in Cuba is for free. You can get a cut, stitched, or a heart transplant, and it costs nothing. Okay? Okay. It's not perfect, but that's very good. And it's already background noise for the young people. They don't care. They want Mercedes-Benz. Okay? If suddenly I tell you, okay, but your mother is not going to a hospital, they don't care. They're not sick. They're not sick. Anyway, but that's background noise. But okay, so we don't charge these developments we have. We don't charge the Ministry of Health for our products. We only, by law, can charge them production cost plus 10%. Okay? Now, so that's the official price in Cuba of many of these drugs. What happens is that when we get into the international markets with these drugs, one of the things they ask is, what's the price in your country for this drug? And that's why they want to pay. They don't want to pay extra. They want to know it's sold at 50 cents. How you can charge me $5,000? So that's a contradiction between reality and the world market. And what you're asking me is exactly the same. The cost, I mean, making one of these will probably cost, I don't know, 50 cents per dose. But then the company says, I spend $1 gazillion billion in research and I need to recover that money. And then the investors that are willing, that invested, that need 35% return on their investment, because those are the sharks in the Bay Area and the Silicon Valley, for example, they want their money. And when you start adding all that, it's $90,000 for a treatment. And I don't know how that will be avoided, but the reality is these drugs will start helping people to control their cancer. And at some point, as happened in one time, for example, HIV drugs. HIV, antiretroviral drugs in HIV have completely changed life for HIV patients. Nobody speaks more about the HIV epidemics, even though it's still there. What happened in the developing countries was it was too expensive to pay for that from the big companies. So they started making those as generics in their country. They didn't care. They violated the patent laws. They violated everything, because one thing is human health, and the other thing is, I mean, I can't pay for that, so should I let my people die? Because I can do it, but so I don't know what's going to happen in this country, but as more and more these drugs are successful, and they have very high prices, something's going to have to happen. Some kind of something will have to cover that if you want to have a healthy population. It's already a big problem in this country, health. There are two things about this country. There are many things I love. I was born here, and I had this, I had this thing about love-hate thing, okay? Because I see so many incredible things, both in ethical and social and liberty terms and whatnot. And I see these great contradictions in education and health. For me, that's the only thing that could put a citizen on the starting line, everybody together. And then they can start running. And then it's on you. Because I cover your health care and I give you an education. And then it's your drive. It's whatever you have inside what will let you turn yourself into a bum or, advance to the future. And I think that there's enough money. I think that there's enough money. But again, I'm getting political and I'm going to be in trouble. I'm going to be in trouble. I'm going to be, somebody from the FBI is going to visit me or something. I don't want that kind of problem. Anyway, so answer to your question, something's going to have to happen. But they will be costly, because now Dendron is selling that vaccine for $93,000. Do you think some others will say, no, mine is $100? That's not going to happen. I have never seen things go down in their price. Every year is more costly. Everything. I bought some jeans. They're like $2 more than last year. How come? They're the same things. They're made in Honduras. I don't know where. Anyway, yes?
Do any researchers in Cuba that you're aware of integrate the metabolic theory of cancer when you're treating patients?
It's very little what we have been doing in that. There's not a big community of researchers in cancer. There's that big center, the Center for Molecular Immunology, that because it was a group in the National Cancer Center of Havana, it has as main task cancer. There's the group I started in the Center of Genetic Engineering, which deals mainly with immunology. And there's a group in the National Cancer Center that deals basically with more genetic things. There's nobody working in that. And that's a field which is very important, because now we know that the metabolic requirements of cancer cells is another target. It was not thought before, but it's another target we had to address. And that means the patient's metabolic requirements and the cancer metabolic requirements. Are we fortifying our body and fortifying our cancer as well? It's a very interesting subject, but we're not working in that. I don't know any group in Havana that's working in that. Yes?
So did you say in section 2 you can actually administer the drugs to a patient that already has cancer? You were talking about the vaccine at the end, but are you also administering the drugs to patients that already have cancer?
Which drugs? I don't...
The ones to build up your immunity.
Oh, yeah.
Okay, so how, is it administered through IV?
Several of the antibodies I told you about, most are given IV, yes.
Is the liver cleansing that out, and there's an effectiveness issue that might be?
It depends on the, antibodies, there's a receptor in your liver, normally, that is called the neonatal receptor, that recycles your immunoglobulins. When you make antibodies against something, they have a long life, biological life in your body, because they're not degraded in the liver. They're captured by the liver, internalized, and released again. And that's because on that, not the two parts of the Y that see the antigen, but the other part of the antibody, which we call Fc part, there's a receptor in the liver that has evolved to utilize those antibodies as much as possible. So it takes the antibodies that are produced by B cells, and instead of destroying them in the liver, they're recycled and shed again to the circulation. That happens to many of the antibodies that we make by genetic engineering. We engineer that part so it can be recycled by the liver, not destroyed by the liver. So they can be doing their job in the body for a long time. That's something that you want for some cases. In others, what we do is we cut that part so that will be rapidly eliminated by the liver or through urine if they're very small pieces. So it depends on what you want to do with the antibody. That's one of the most exciting fields now of what is called antibody engineering, is trying to change parts of the antibodies to keep them, to get them to penetrate better in tumors, to be eliminated faster or slower from circulation. That is a very exciting field now of work. Yes?
Do you foresee that Cuba will become a destination for medical treatment?
It is already. There are several clinics there that provide, I would say, very nice update medical treatment for many patients in Latin America and even in Europe.
How about for this kind of?
I know that the National Cancer Center that works with us, many of these clinical trials we do in combination, there's a whole system of certified hospitals that are qualified to make clinical trials in Cuba. I mean, that's high quality stuff. And in the National Cancer Center, they already have like 2 wards that are only destined to foreign patients that come to get cancer treatment in Cuba. But of course, the treatment has to be approved. They will not get into clinical trials. It has to be an approved drug, an approved treatment. Yes. There are some interesting things. I mean, you gotta understand that cancer is a very sensitive problem, and there are many people trying to do things and to cure cancer, and the motives are genuine, are real. I mean, it's not that we're trying to make money. We're not. People are trying to help some ways, and everybody has ideas. I think that one of the most important things is that there are many things we don't know about our body. So if you have a scientist that tell you that this is the absolute truth, that guy's nuts. This may change in 2 years. Of course, it will not be 180 degrees, but we will refine some of that knowledge, because that's what has been happening for many years now. We're refining our knowledge more and more. So that means that there's space for theories and ideas that come from different angles. What I think that is needed is for you to understand that those things have to be tested and proven under the rules that now show us what is real and what is not. I was talking with Candace and her husband today how difficult it is now to make a clinical trial. Why do we need so many patients? Because we know that there's something called the placebo effect. The placebo effect is that if this gentleman has a headache, and he knows that aspirin normally kills his headache, and he doesn't have aspirin, I give him a sugar tablet and say, this is an aspirin. His headache will go. It won't go forever. It won't go every time he does that. But there's some interaction between, it's psychosomatic, between your well-being, your cerebral well-being, and the stimulation of many mechanisms that start up here, and how your body reacts. So you know now that in any group of people that you test with new drugs, whatever drug it is, or procedures, you should account for 10% to 20% of people in the control group that giving them nothing, just telling them that they are going to go to a hospital and get a special treatment that may cure or not, if they're in the right group, just telling them that, okay, they will improve. They will probably not be cured, but they will improve, and sometimes substantially. And that's why we need then hundreds and hundreds of people in a trial to be able to tell you, the end users, the people that are going to use this drug, that that drug is effective in 80% of the population. Because it's not a simple question. I mean, it's an ethical question. When I tell you that my vaccine works, it's not because I told you about this 8 people there, which for any medical doctor here or any oncologist that you have in the audience, there's several very, very tough tumors there. And 4 years without getting any treatment, only the vaccine, that vaccine is probably it's doing something. But that is anecdotal. I haven't done an experiment with humans in the right number and with the right controls to be able to tell you that that vaccine is working. It would be unethical for me to tell you that. That's what we call an interesting result. And of course, I wanted that vaccine. Oh, yeah. And well, what you individually do is what you do. So along the time, I have seen many theories. And what I try to stress is that somehow, whatever you do has to go to a testing ground. And a testing ground that moves along the rules that have been established by many countries after 50 years of understanding how to do clinical trials. This is a serious thing. It's your confidence. It's when we speak about, I have a pharmaceutical, something that works, it has to work. And even then, listen, how many drugs are recalled? You know about that. Why? Because even though we make phase 3 clinical trials with thousands of patients, when 1 million people receive that drug, some effects that were not seen in 1,000 because that was not the frequency start appearing, and maybe you have to recall the drug, even then. So it's a tough job to prove that you have a new drug or a new procedure. And it may be that this 30 patients or whatever were cured, but we will have really to go there, see what happened, see his procedures, and then say, okay, there's something there that has possibilities. In fact, let's do a clinical trial, a real clinical trial. That's the only thing I can tell you. Yes?
Is there any line of research or researchers who are attempting to manipulate the placebo effect, the ability of the body to cure itself, to activate the immune system through, I don't know, some sort of...
Well, there's a field now very interesting in immunology. It's called neuroimmunology. Neuroimmunology. Because there are many things that are released in your body because of signals that come from the brain. And we're trying to know a little bit more about that because of the placebo effects and many other things. We thought, that the brain was for, fantasizing and thinking and writing and whatever, and the rest of the body did something else. Now we know there's this huge connection, and we're still learning. And I know when we will be able to control these things, we'll find other treatments, and we will add some extras to our vaccines and to our drugs that will give us that plus that is the placebo effect, that psychosomatic stimulation of your immune system or your metabolic system. It could not be an immune problem. It could be just a metabolic problem, what we have there. Yes?
On 60 Minutes, the show 60 Minutes, they injected the polio virus into the brain, into the tumor in the brain, and they showed that, they were actually curing some of the people that have this tumor. Is that any work that you're doing in Cuba?
No, we're not using, in this moment, there have been, one of the things that we're trying is to transmit new genetic information to the tumor cells. Genetic information that will tell them, die. Basically, that's the thing. So there has been a lot of work over many years of manipulating some viruses, infectious viruses, in a way that they will not produce their disease, but they will be able to infect selectively tumor cells and give them additional genetic information. So that genetic information will say, please die. because they're signals. It's called apoptosis. Our cells die normally because they're programmed to die. And we now know many of the genes that produce that death. So we put those genes or those signals into a virus and we inject them, and if we are able to make that virus infect selectively the tumor tissue, we can get that effect. So that's what's happening with the poliovirus and with the influenza viruses and with other types of viruses as well. That's something that is being done. We're not working in that in this moment. Yes?
Do you have any statistics on Cubans' autism issues? You had all those statistics at the front. Are you so autism issues that we are here?
No, I don't have that information. It's interesting because there's a Cuban FDA. And the Cuban FDA, of course, is tougher than the American FDA. Because if you want to sell your products in the first world, you got to be tough in your regulations, because you're going to be scrutinized and say, how come this, low-class people, Indians or whatnot, are going to give us something to us, white people, developed countries. Anyway, so our FDA, our Cuban FDA is very tough, and we have been discussing the effect of some adjuvants lately, because there's a lot of discussion about the effects of aluminum on autism and other things. To the date, I have extensively reviewed what is published. And to me, it has not been really shown that any of these adjuvants impose a real problem. There may be cases, but it's very difficult to pinpoint the cause. Now, that doesn't mean that that is not true. Because, of course, if you inject the aluminum salts to some primates and to other animals in high quantities, there are neuromuscular problems, and that we know. But that doesn't mean that at the doses we use in kids' vaccines or even in adult vaccines, the same thing is going to happen. And then there's always that kind of balance between risk and damage. And if you're dying from cancer, are you going to worry about autism? Give me the vaccine, please. I'll deal with that later. It's a serious problem, and we're examining that, and we're discussing that very seriously in Cuba. But to the moment, I can't tell you, I haven't checked the statistics. It hasn't shown, at least in the reports of the Ministry of Health, that we have a huge autistic population of kids or whatnot. It hasn't shown up. That doesn't mean that we don't have it. Right? That's what I can tell you. Yes? Yes.
I thought this was a very informative and well-delivered talk, and very extremely nice, and thank you very much. And as a person who is, I've gone through a year and a half of chemotherapy right now for colon and liver cancer, and we're about to leave that regime, and my oncologist urging me very much in the direction of immunotherapy. And my question has to do with whether or not the rate of improvement and recovery and application and so forth, what it could be compared with what it is, and is there barriers that are in the way of holding that back? It's kind of frustrating it takes this long for this to avoid all the snake oil stuff and so forth. We have to agree with that. But is there anything that can be done to speed this up, or is it going about as fast as it?
Well, what I've seen is the following. The FDA has a fast track now, so you don't have to go to phase 3. If you make your phase 2 trial, after showing that there's no toxicity, you go now to patients and try to show some effect, and you select a niche of patients that have a disease that you know that available treatments don't work, and you get there some outstanding results, then you can get it's not a partial approval, it's a temporary approval, and people can start receiving that drug with the reservation that the company has to go anyway through phase 3 trials. So that's a way of trying to put in the hands of people that need these new drugs the drug before it's before it's completely proven. It's a risk, but there's so many people asking the same question you're asking. And when you see some outstanding, really outstanding results, as those we see in melanoma and lung cancer now with these drugs, that's not, I mean, it's not increasing for a month your survival. I mean, it's huge what is happening with these drugs. So there's something there. And I think it's a duty also of the regulatory bodies to accelerate the discoveries as much as possible. But always you got to follow some rules. Because I could be telling you this is like the promised drug and it could be toxic at the end. So there's this balance always.
Thank you so much, Jorge, for
Well,
this.
I'm thanking David because he convinced me to drink a Red Bull before. So I have this energy.
I know, I didn't see you this energetic during the week, that Red Bull. Let's promote that Red Bull. So thank you so much for being here with us tonight and this very informative and stimulating presentation. And I'm sure that everyone feels like I do, that we've learned an enormous amount. So once again, thank you, Jorge, so much.